It's wonderful to be here with so many people to see. I'm feeling a little awkward because all these couple of years been giving talks on Zoom. So it's a little awkward actually to move around and give a talk. So I'm going to talk about the black hole evaporation problem, attempts to solve it in the SYK type models coupled to a conformal field theory. And this is, okay, so this is some ongoing work with these authors, Advait and Anurag and Gautam. And I will, I'm happy that Victor and Omkar gave talks before me. So I will very quickly review the basic material to lead up to what we are doing very quickly. So SYK model, Sachdev, E. Kitaev, the model of n real fermions interacting in groups of 4 or more, and the interaction is random. The motivation of this goes to condensed matter physics to understand the physics of systems without quasi-particles. So here is the model. It's a very simple model. The degrees of freedom are basically some gamma matrices, and the dimension of the Hilbert space is 2 to the power n upon 2. And if n is large, this is a large Hilbert space. So this is the Hamiltonian, and this is the expectation value of the random noise, which is Gaussian, and the Gaussian is given by this formula. Okay, so I'll just summarize very briefly. Okay, so some of the more important points about the SYK model are as follows: that in the limit of large n, where n is in a sense the largest number in the problem, and for large j, which implies low energy in this problem, there exists an infrared fixed point and an emergent infinite dimensional symmetry. Okay, so this is a very important point. And the low energy degrees of freedom in this model are just these maps from the real line or the circle into a space of functions, which is, and this is the set which usually we call dFAR1 mod SL2R. You've got to quotient out SL2R. I won't be explaining any of these reasons, obviously, in a 15-minute talk. And the effective action of the low energy degrees of freedom is the well-known Schwarzschian. And these are two very important results, actually, for which why this model is so interesting to us is that it has a density of states which is given by this formula, and it exhibits maximal chaos. That is, the out-of-time ordered correlators grow in a certain time range, and the Lyapunov exponent is its maximum value, 2 pi upon beta. I have put h bar equal to 1 in these formulas. Okay. On the other hand, there is a dual theory of gravity, which everybody is familiar with. Everybody means who works in this area. It's called JT gravity, Jakiv Teitelbaum, and it has a metric and a dilaton and some matter fields. And it comes about by a dimensional reduction of near extremal charged black holes in, let's say, 4 dimensions, for example. There is another theory of gravity in 2 dimensions, which is what's called Polyakov gravity. It's a very non-local version of the Einstein theory, only consisting of the metric. And if you look at this theory is born out of the study of the co-adjoint orbits of the Virasoro group. And here too, in this theory of gravity, the degrees of freedom are identical to the SYK model at low energies, and the gravitational action is a boundary action. And this is the Schwarzschian, and this is the equation of motion. And you can now, write down a class of metrics actually in this theory, which can be generated, let's say, in Poincare coordinates by essentially a diffeomorphism symmetry like this. Okay, so all this is very well known, and one important solution is this famous tangent hyperbolic, which describes a black hole in ADS2. This is Lorentzian spacetime, and this is thermal ADS2. If you just take an analytic continuation of time to imaginary time. Okay. All right. This is the picture. So this is a picture of our space-time, this is ADS2 in some global coordinates, which I have not mentioned, just hidden them. And once again, this is our famous function, which describes the black hole in Omkar coordinates. Okay, that's important. And if you look at F dot, which is the central object of our interest in this investigation, it goes to 0 as t goes to infinity, and back to these coordinates, you find essentially that the curve F, this curve essentially, is the dynamical curve that gives the dynamics of the JT gravity or the Polyakov gravity or the SYK model identically. The important point over here is that this curve near the boundary is given by these coordinates, obviously, f of t times z, which is very near the boundary, and times f dot. And this is a very important point, that if f dot vanishes, the observer who is using these coordinates, the space-time ends simply. So the vanishing of f dot is to be understood as the formation of a horizon. This point is very beautifully explained in the paper by Kurkulu and Maldacena, actually, from which I have learned it. So the key point is that f dot equal to 0 signals the appearance of a horizon in the bulk. And if f dot is always positive, not 0, then the space-time has no horizon. All right. Now, how do you manufacture a geometry without a horizon in the SYK model? You can't. You cannot do that simply. It always describes at finite temperature a black hole. So Kurkulu and Maldacena found a perturbation of the SYK model such that in the solution of that extended model, f dot is always positive and there is no horizon in the geometry. And they did this by introducing, on the face of it, a relevant operator, because the infrared dimension of the fermions here is 1/4. And this operator is written like this. And these are a bunch of numbers. These numbers are basically eigenvalues of the spin operator in the microscopic theory. All right, so I give you a bunch of numbers, plus, 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 up to 2 to the power of n upon 2. And what is the idea? The idea is as follows. The idea is how to compute, when you extend the SYK model by this new operator, how to compute its low energy projection. And this is done as follows. So first you look at these states, which are made of the eigenvalues S1 goes plus or minus 1 of the SYK model. Okay. These are the basic states you can form in the SYK model. Then you have a low energy projection, actually, where 2L is beta. This is also very standard stuff. And we are working in the regime, and this is very important, that beta j is much, much greater than 1. All right, that's why this projection really projects you onto low energies in this problem. Now, the important point is that this BS that I'm going to consider in my discussion is precisely made of exactly those eigenvalues which the Kurkulu-Maldacena operator has. And it is only in such states that we can discuss some sort of low energy projection, and also the fact that this low energy projection can be written entirely in terms of the function f of t, these maps. Okay, so this is a state-dependent operator, which is along the lines of Papadopoulos and Raju some time ago. And if you do the calculation, you will find that the Kurkulu-Maldacena operator gives rise to an additional term over here, which is just exponential of phi upon 2, rather than exponential of phi. All right, so this is a important result, and using this result and a time-dependent epsilon, which gives rise to 2 quenches. Some time ago, we studied black hole formation in this model, and we could follow dynamically in real time black hole formation. And we could also calculate asymptotic temperature. I'm sorry, I forgot 1/2 over here. That's important. Yeah, so this is the temperature in terms of certain parameters.
You have 5 minutes left.
Sorry?
You have 5 minutes left.
That's all. Oh my God. All right. Okay. Sorry. I think I'll go very fast now. So coupling a bath, the conformal field theory to the black hole, this is some work in progress. So basically, what you do is, this is bad, that you have some NF free scalar fields, and you couple them to this particular operator in the SYK model, and then simply, okay. This is the coupling over here. This is the free fields, and this is the original SYK model perturbed by this Kurkulum-Aldacena term. So you do this. This is somewhat like the Kondo model, where you have a dynamics at a point, and is coupled to a two-dimensional conformal field theory. All right. So what we want to study is the density matrix for large times. So we want to compute some operator, expectation value of phi. So this is a very standard thing to do. And we have heard several people talk about it, that the evolution of the density matrix is given by this type of simple time evolution. And that leads us to consider what are the initial states we want to talk about. So initially, we want to talk about a black hole state. This density matrix represents that. Then this is another state, actually, of the conformal field theory, which is given by this type of state called de Calabrese-Ricciardi. You can explicitly compute all of this, and this turns out to be a squeeze state. And in the regime when the so-called SYK temperature is much, much larger than the temperature of the conformal field theory, we can write down the standard Schwinger-Keldysh formulation. And as we heard in Omkar's talk, you have a Feynman influence functional. So this is the influence functional you compute. It's all very complicated stuff, actually, but can be done and elementary. So the effective action is given by this, and this is the influence phase. And so now, once you have this, you turn on the crank and you try to compute. So very convenient to go to what are called Keldysh variables. And you can write down an equation like this. This is the, so what you do is the quantum part you compute in perturbation theory to phi square order and phi q square order, and you essentially have a Gaussian noise. If you have higher order terms, the noise won't be Gaussian, it will have corrections. So this is the complicated integral equation you have to solve, and this is the noise correlation. So this slide is a result, actually, of a mathematical problem which we would like to solve. Now, this problem is rather hard to solve, even consulting a lot of literature. And so what we did is, in order to do the numerics, we converted this problem into a problem of a third order differential equation, where the memory term is gone now. You see that integral memory term was there, that's gone. And the correlation function is given essentially by this. Still not very easy. One thing which I would like to do is, introduce auxiliary variables like position, momentum, and acceleration now also, to write down this third order equation essentially as 3 first order equations, and hope that we can compute a differential equation for the probability of xp and now also the acceleration at a time t. So this would generalize the Kolmogorov-Fokker-Planck equations, actually, which are very well known. But the problem here is that the noise is more complicated than, because it's not short-ranged. Okay, so for times which are much, much less than n, one can actually neglect the noise term. You may have observed that there is a 1/n sitting in front of the kernel there. And one can do a numerical calculation, actually. So, oh God, this is very sad. All right, the important point is that this axis is the phi field, and this is time. And at large times, what happens is that the phi field settles down to a certain fixed value, okay, with oscillations around it. Okay. Sorry. All right, so now what is the significance of that? So numerically one can see that the asymptotic solution approaches a certain value in terms of certain parameters plus oscillations. Now this means basically that asymptotically f dot, which is exponential of phi infinity, is not equal to 0. Okay, that's very important. That's what we were after. That the geometry without a horizon has appeared now, even though we started with a geometry with a horizon. And a physical understanding of this effect, this phenomena, can be understood as follows: that you take the equation of motion and you can write down energy function. If the path coupling is not there, of course, this is conserved. And you can compute its time derivative, and it's strictly negative. You can show that, very easy. And what you do is you extract this effective potential and plot it numerically as time goes on. In a sense, this is the main plot of this talk, that is very, very interestingly, what happens at time t equal to 0, you have a potential, effective potential, which supports a black hole. And as time goes on and on, this potential dips over here. And the dynamics is then constrained to some region, and it's bounded. If it's bounded, f dot cannot be 0. And this is another way of seeing that the horizon is gone. So this is the summary. It was very fast, I know, but so the SYK plus Kurkulu-Maldacena coupled to a conformal field theory can model the dynamics of black hole evaporation. And we are able to do this math, I mean, numerically, for times which are much, much less than n. And because of that, for a system like this, the fluctuations are suppressed, and I gave you the solution. But for times of the order of NL, fluctuations cannot be neglected. And one has to learn to solve these complicated stochastic differential equations. So thank you, and sorry for being over time.
Thank you, Spenta. We have time for a couple of questions.
I can't.
Can you hear me? No.
Yeah.
Okay. Yeah. So I was wondering, since you don't have a horizon at the end,
Yes.
like what is the system? Is it just
ADS2. Just ADS2.
Okay, but is it like a wormhole, or is it just
no?
How do you think of it?
No, there is no wormhole here. I mean, there might be an understanding of this in some other language, but this is simply doing the dynamics actually. So f dot will simply keep on going straight. It will never hit the 0. And so there is no horizon. That's the point.
But isn't it similar to the Maldacena-Chi solution of the eternal traversable wormhole then? When you have this, so you have this boundary that goes constantly in time?
So, good point. So I'm working with half space actually.
I see, okay.
Yeah.
I see.
So I have actually used the Z2 projection. I didn't want to discuss all those details.
I see, okay.
Yeah, introducing the
then you only have one side, okay.
One-sided,
see,
yeah. Okay. You can actually choose your state on the left-hand side to have this Kurkulu-Maldacena operator in the type
I see, okay.
it is. Yeah.
Okay, thanks.
Maybe one more quick question. Yeah, Rajesh.
Hi, Spenta.
Yeah, hi.
So thanks. I didn't completely follow, but if you increase, maybe you said it, but if you increase the strength of that Kurkulu-Maldacena coupling, is there a qualitative, some range where something happens?
Yes, it's a very important question. You see, the Kurkulu-Maldacena operator is, in a sense, a relevant type operator, but you want to still make use of the infrared physics that I'm using, the low energy degrees of freedom. So that coupling has to be of a certain size. It has to be small, but over here, for example, in their original work, it has to be small but greater than 1 upon beta j, because only then the potential will have a dip. But all those things we have taken care of very carefully, actually, including cutoffs and everything. And these equations are right, and wanted to just get the right equations first, and then see what we can do.
That means, if I understand right, this is the solution in a range between 1/βj and there's some upper limit where it might just float to some
Exactly.
other.
Exactly. So this is
effect.
why the coupling to the bath, those numbers, then the number of flavors to the number of colors, all those numbers somehow have to conspire to give you the correct physics actually. And it is possible to do that. That's important.
Let's thank Spenta again for this wonderful talk.